So for step 8, we are tasked with using Newton's second law to make equations that we can then integrate to find velocity time equation and velocity position equation for terminal velocity. And part C is determine the terminal velocity for each profile. D, use parts A and C to find fractional percentages of terminal velocity. This one is for time, and part E is for distance. So I made a free body diagram, and to make the signs less gross, I guess, I made the convention that up is down and down is up. So you can see the force of drag is equal to kV plus B, and you could see the force versus velocity graphs from step 5 through 7. So that's, oh man, it's not focusing very well, is it? Yeah, so that's what this line is. This linear fit of the data of the force versus velocity graph. So that's what this is here. And you can see that in my Newton's second law equation, mass times acceleration is equal to mg minus kv plus b. Plug that in there. And then I actually turned kv plus b into k times terminal velocity minus instantaneous velocity. You can kind of see here how I justified that step. Ma minus kv plus b equals k times terminal velocity plus b minus kv plus b. You know, got this, factored out the k and turned it into this, so it's more convenient for integration. So then I, divide through by m, turn a into dv dt, because I'm trying to get an equation for velocity for time. So I divide the m through and then get the equation into a form that's not disgusting for integration, basically. And then I integrate this and I get the integration. I get v of t is equal to vt times 1 minus e to the negative t over tau. And in reality, tau is k over m. But since it's in the denominator, it becomes m over k, and I call that my time constant, so it's easier to plug and chug later when we're looking for values. So basically, part B, nothing special, same deal really, just a little bit harder of an integration. You could see my function for position here, and then there's a fractional version of these equations, and there's one for time here as well, so that we could do steps D and E, which are requiring the time to reach 50%, 90%, and 99% of terminal velocity. And part D is for time, and part E is for distance. So this next page over here is actually the actual values. So part C is pretty straightforward. So you can see that when acceleration is 0, going back to my original equation, 0 equals mg minus kvt plus b. Solve for vt, you get terminal velocity is equal to mass times gravity minus b over k. And then I solved for the terminal velocity for all the shapes here: sphere, golf ball, cylinder, long side, cylinder, face side, block, large side, block, thin, face. And then for parts D and E, I used that fractional equation to find the time it takes to get to 50% terminal velocity, 90 and 99% for the sphere, golf ball, cylinder, cylinder face, block large, block thin. And then this down here, step E, is for the position.